Hello, we're working currently with vector equations and linear equations in 3 dimensions. And so what we're looking at now is given two lines in Cartesian form, we first need to find the angle between the lines and then to determine if they intersect. We talked in class about how you can in fact find an angle between lines even if the lines don't intersect, because we're really just talking about the vector position and direction instead of the lines actually connecting. So anyway, that didn't sound fun to say. Alright, determine whether the lines intersect. That's the second piece, and that's the main reason for this video, just to show you sort of an elegant way to approach the process. But first, we need to work with these equations instead of in Cartesian form, in vector form. So we begin saying that each of these is equal to a parameter and solving for our x, y, z in terms of lambda. This, then, is what's known as parametric form, and we convert parametric form into vector form simply by writing our parameters as vectors. Now, in the second case, we actually have sort of an advantage. This makes things a little bit easier in the long run, and you'll see how. But what I know is y equals 1 plus 0 lambda. In other words, I can't set all of these equal to lambda because this can't be solved for lambda. But we should at least recognize then that y is a constant at 1. In other words, the y is unaffected by the value of lambda. Whatever lambda is, y is 1. So this again is actually a good fixed position. So here's x, y, z then equaling -1, and then we're going to have the plus 3, and we put a 0 in for the direction vector because that's not going to change the value of y. And that's our vector. That's our vector, Victor. Now, the 5, 1, -1 is the direction vector for one of the lines, and 3, 0, -1 is the direction vector for the other. So to find the angle between, I'm going to use the cosine formula, that is the dot product of the direction vectors over the magnitude of those vectors product, which gives us the value of theta at the inverse cosine of 16/270, or 13.6 degrees. It's important to get a visual and determine if this is at least reasonable. And when you look at the way the lines, I wish I could rotate this image, but when you look at the way the lines pass each other, it is clear that they're not very much like at a right angle, clearly not perpendicular, and a small angle here seems appropriate given the picture. So I say not a large angle. At least I know I looked at it and I get what's going on. Now the question of intersection. Remember the best way to think about this in terms of just cognitively understanding is, where do the shadows cross on the xy plane? So what we have is these two lines are floating in space, but if you shine a bright light over here and cast a shadow, it will look like the shadows of these lines will definitely cross somewhere. So the first job would be to find out where would the lines cross on a shadow plane. Now that shadow plane, I chose the xy plane as my shadow plane, which is the gray surface right here. So we're shining a light on top and finding out exactly where are the lines crossing on the shadow. Then we're going to project upwards to see if their z values are in fact the same at that shadow intersection. So this is the part I wanted to show you then. I was going to add to the fact that I chose xy, but you can choose the xz or the yz plane. Any combination works, but I chose this for a reason, as you'll see. So I have the two-dimensional lines in vector form, and I'm going to find their intersection. And I want to point out that this 0 in the lambda position for the y value is actually a really big advantage, because it prevents me from having to go through all of that system of linear equations kind of thing. Because as you can see, 1 plus 0 lambda, or just 1, is equal to -2 plus 1 mu, which is mu equals 3. Done. So I go to the second step, which is to go to the x parameters, and there I can find an equation that also has lambda and mu in it, but I've isolated mu at 3. So again, what this 3 is saying is, after 3 iterations of time, if you will, the turquoise line, or the blue line, is going to be over the intersection position. So what time is the purple line going to be over the intersection position? That's what we're trying to find out. So at 3, that means the lambda had occurred. Holy cow, that was a lot of writing at once. At 3, it means that lambda occurred at 6 1/3. So if we're looking at this in terms of time, 3 minutes after starting, the first line reaches the shadow intersection. 3 1/3 minutes after that, the purple line will reach the same spot on the shadow. Here's where I would normally have said go back into these two-dimensional vector equations and determine if that does indeed happen. That is to say that they intersect at the same location at different times. But it might be more efficient to recognize now we can go to the three-dimensional vector equations and use the values of lambda and mu, and we can judge two things at once. So you'll see I'm just cranking out the busy work here. In both cases, I just took the value for my variable, in this case lambda 6 1/3, put it in for lambda, and found the exact location at 6 1/3 minutes per second, let's say. Here we have 3, and we put in 3 for the mu value and determine its position. Here's what we recognize. They have the exact same shadow, 18:1, 18:1, so that's a good thing. However, the z-coordinates at that point are different, therefore the lines do not intersect. If the xy positions don't match, then you made a mistake. So that's a self-checking format. This here, the xy, if you used xy up here, then your xy here had better match up here. If they don't, then you solved your system wrong. Guaranteed that's where your problem would lie. You solved the system wrong, probably dropped a negative or something silly like that. So, thanks for watching. Have a great day. Yada, yada, yada.